So we are needy. We at Mozilla have been doing browsers since '94 in some sense, and I did the first JavaScript implementation in '95, and even though the language has got a lousy reputation because of pop-ups and things like that, it's a it's VM-based type-safe language. Not much declarative about it, but it's still spread like cold. You probably know what Mozilla is. I just want to run through some things here. The striking things to me about Mozilla are that we're alive still. We're actually getting a lot of uptake. We're having some successes. And I think a lot of it has to do with the use of high-level languages. It certainly has to do with our being cross-platform. We don't count on any one platform. We want to do well on Windows for sure because it's on so many PCs, but we're also on Linux and a bunch of Unixes and Mac. We dropped our OS 9 support the other year. That was traumatic. But we're pretty portable. BIOS, there's some Amiga port enthusiasts out there. So we have a very portable code base. A lot of it's in C++, but all the user interface code is JavaScript and a bunch of XML languages and some HTML and cascading style sheets. And we're getting SVG implemented. It's big specs, so it's partially implemented. The useful parts are coming along. This is a real platform. It's not something we intended to be a platform for the world. We did it for ourselves because we didn't want to write a bunch of native front ends for each platform. We wanted to have a better app development framework based on web standards. But it turns out that a lot of people want that too, so people are building apps on Mozilla, the code base for the platform. And that means that we're having to document things and apologize a lot and fix things up. And I think for the first 4 years of our life, sort of childhood and adolescence, when we got to Mozilla 1.0, we had apps that people said finally didn't suck. And after that, we've really been improving the apps, and we're ready to do a platform push for Mozilla 2. And it's hard. It's a dessert topping and a floor wax, and you have to do both well. But with open source, we have a broad community of people we can bring to bear on both problems, volunteer writers and so on. One of the cool things that happened early on was Active State funded some work for themselves, and they had their own desire to build a Perl and Python IDE, and they did that implementing a lot of the front end in Python. So they actually constructed a bridge from Python to XPCOM, which is our component object model. It's a very simple Microsoft COM-like thing, add ref release, query interface. And that bridge is not bundled with our products, but it probably should be. I think that if we did, we would have a broader platform. We also had Java for a long time integrated, but only as a plugin, if you can believe it, with some extra ad hoc APIs. And it's never been successfully bridged with XPCOM so that you can call between C++ and Java. You can implement interfaces in either language and not know from the caller which language the callee is implemented in. I think IBM, somebody in Austin, is actually finally getting a full Java XPCOM bridge going, which is great. And we have a mono bridge, believe it or not. I think it's mono-specific. I think our goal, though, at the end of the day, is that any ECMA 335 implementation with some sort of non-standardized but de facto standard interfaces can be used. So we shouldn't be able to use CLR on Windows.
Could you elaborate a little bit what all this bridging can do?
Sorry?
What all this bridging can do for you? So this bridging of the mono and bridging of Python. What it means in practice, in how deep is that bridging?
The bridging means that you have to be able to XPCOM is the lingua franca, so it's like COM. It has an I-unknown root interface, which has query interface, add ref and release. We call it NSI supports. Don't ask why. The NS was for Netscape, but you're supposed to think namespace now, just poor man's C++ prefixing. if you can implement that and the fundamental types, which are basically your portable Java C-like types, and you can handle a few other things like the way we handle thread safety. We have, besides the interfaces, these abstract-based classes, we have some notion of class info, sort of a co-class idea, Microsoft calls it. So if you can have a little extra metadata associated with your components, then you can implement a component in any language. You can call it from any other language. And the only way you'll be able to tell is performance. This diagram shows what's going on. There's light blue bridging going on. Some of it's embedded bridging. The bridge between JavaScript and XBCom is called XBConnect. There's a lot of weird historical jargon here that I apologize for. But if you just look for the light blue, you'll see the bridges. And the reason that JavaScript XBCom bridge is so central is because it's historically hacked in a number of different ways. And it's not something that you could substitute another bridge for. JavaScript is the default scripting language on the web, and it's tied into DOM directly. So that it has special status, for better or worse. And that's enough of that. So this is a virtual machine conference. I thought I should talk a little bit about VMs. I'm an amateur, and I've been busy herding cats, managing the project way too much to have time to read enough papers to keep up. But I wanted to let people know that we do have 2 JavaScript VMs. One of them is written entirely in Java. It's pretty successful, and it's called Rhino after the mascot on the O'Reilly book. And it's successful in server settings. It generates class files, and with a good JIT, you actually get better performance than with the other engine we have. SpiderMonkey is that other engine. That's the one that's in all Mozilla apps. That was the one pictured in that cake diagram. It's pretty old. It's fairly hacked over. I've had to hack it in haste in past Netscape lives and repent at leisure. And it's actually pragmatically evolved along a number of axes in ways that might be interesting to talk about here briefly. One of them is that it is thread safe. Mozilla is not that multi-threaded. It has some I/O helper threads, but the layout code is all single-threaded. And I think, given that we're using C++ and a little C, we're probably better off for that. We have a large audience of hackers, and the bell curve is not going to do well with manual mutual exclusion and condition variables and so on. But the JavaScript language implemented by this SpiderMonkey engine has been embedded in servers in multi-threaded settings, and it's used in VXML services, really big ones. So there's all sorts of crazy, not only multi-threading, but large-scale scripting going on, giant switch statements for state machines that required me to add span-dependent jump instructions, and the thing was way beyond its design limits, which is probably a victory condition. One particular thing here I wanted to mention was that JavaScript was meant to be this simple model, so the programmer is not aware of threads and views scripts as running to completion unless explicitly using continuation style programming, essentially, with the DOM, set timeout, things like that. That makes it easy for us in the API to the engine to require the users of that API to bracket their run to completion chunks of API calls and native code, and to call out their preemption points. And once you do that, it's not too hard to do a number of optimizations, including if you can amortize the cost of locking with the GC at those request boundaries, then all the object locking that you would need for transparent thread safety in the middle of those execution chunks can be made lock-free. It can completely go away, just via a comparison without memory barrier or anything. And we do that, and we use that kind of request execution model also to do some string optimizations. It turns out people go crazy on the web and even in our apps, and they write a lot of string concatenating loops of various kinds. Here's sort of reduced in Vacuous example. And with garbage collection, we were piling up a ton of intermediate garbage. But with this knowledge about what objects or strings are possibly escaping to other threads through that request barrier. We can optimize to reallocate buffers and share prefixes of buffers, and we do that. And that was a pretty big win. That's about all I have to say that might be interesting at the implementation level for VMs. Really, I want to get back to our needs. We benefit greatly from using virtual execution environment. We have cobbled one together sort of from the dawn of the web without being able to use Java, which would have been nice. I could talk about that later, about why we haven't written the whole thing in Java. We have a lot of problems with leaks. And I'll show you a chart if I can get to it. Let me try to tab to this link. We use automated build system called Tinderbox, and we run some leak tests, and we give feedback promptly. And we supposedly close the source tree and back out the offending change when something goes wrong. But things do go wrong, and this last big spike took some of the best brains in the project to figure out. It's just mundane stuff. The bug was a badly merged patch, if you can believe it. But for a long time we were diagnosing big object graphs and trying to find the strong components and compute the leak routes, and it was all stupid and wasted because we really just had to read the patch more closely and notice that one critical line was. But like I said, I'm a practitioner. I'm not theoretical enough to think if there's a better way. We're stuck with the current code base. We're trying to